we have been discussing on flow past bodies of various shapes, and if we recollect that in our previous class we identified that there could be bodies of different shapes which are generated out of considerations of various elementary flows if you start with a potential flow consideration. Maybe one of the important things of concern for such cases is that if you have a wall, or if you want to represent the existence of a wall, how do you represent that? For example, say you have a wall like this, and say you have some source located at this point, say A, which is basically on the y axis, where wall is the x axis. So you have a source of a given strength located at A. Wall is not given to you, say only the location of source is given to you. Now you are told that now we have a wall, we should have a combination of superposition of flows which would represent the effect of this wall. So how do we do that? Given this source is already existing, we have to keep one thing in mind. What is that? We are talking about a potential flow in this example. When we are talking about a potential flow, it means that no penetration boundary condition is the only boundary condition that we have to satisfy at the wall. So if you have a source like this, see the source radially emits flow in all possible directions, that means it also emits a flow radially in the downward direction. Now from this, do you have a clue that what we should do to make sure that there is zero normal component of velocity at the wall? No, phi equal to 0 or rather streamline or a stream function equal to 0 represents a body of a particular shape, because the surface of the body is a reference streamline, that is true. But how do you ensure that with this physical example? What more you have to get to ensure that yes, this is such a line where you have no penetration? So it is the inverse problem. It is not that you generate a body of a given shape, given a body or given a wall, what extra thing you need to have with this to ensure that you satisfy no penetration at the wall. Let us say this is a plain wall, just as an example. Just think like this, it is a very common sense thing. Say you have just like a reflection, you have an image source located at this point. So if you have an image source located at this point, see that it will also have its own radially diverging field, and one of the velocity directions is this, it will be perpendicular to the wall. So if these two sources are of equal strength and located at equal distance from the wall, then these two effects will nullify each other to have resultant normal component of velocity 0 at the wall. So this is a very simple concept, but may be implemented in practice very easily. So it will now become a superposition of a particular say source and an image source, where the image is with respect to the reflection as if the wall is like a mirror. So a superposition of that. So this is known as method of images, very convenient method, and one can generate the effect of the wall using this. Now we have also discussed that not all flows are potential flows. In fact, no flow in reality is a potential flow, but potential flows are important because if it is a boundary layer theory that you are applying, then outside the boundary layer you may apply the concept of potential flow, and whatever pressure gradient that you calculate out of that, the same pressure gradient is imposed on the fluid within the boundary layer. But because of the existence of the boundary layer, you have the viscous effects also important, and that dictates what should be the drag force on a body. Of course, if you have very high Reynolds number flow and a bluff body or a body of such a shape that flow separation occurs quite quickly, then the form drag or pressure drag remains to be the more important concern than the skin friction drag, and then the drag coefficient sort of may become independent of Reynolds number at a very high Reynolds number. Now if you have say a flow where viscous effects are important, then you represent that with a drag coefficient, where the drag coefficient is a combination of the skin friction drag and the form drag or pressure drag. Now the drag coefficient will have in general a dependence on Reynolds number. In certain cases for very high Reynolds number flow, because the form drag effect is very important, so it may become virtually independent of Reynolds number, but otherwise because of the skin friction effect it becomes a strong function of the Reynolds number otherwise. So let us look into one or two problems where we illustrate or we try to see that what are the consequences of that. So let us consider one example. Say you have a flat plate, but this plate is oriented in a bit of a special way. The dimension of the plate is given. The dimension of the plate is given as the height is delta and the width is L, and you have a free stream velocity. The free stream velocity is not a uniform velocity, but the incipient stream is like a boundary layer already developed by itself, and assume that this is a turbulent boundary layer where you have the velocity profile given by u infinity is equal to y by delta to the power of 1 by 7. This is given. You have to find out that what is the total drag coefficient or the net drag coefficient because of the interaction between the fluid and the solid plate. What is given is that for a turbulent flow you may assume that the CD is 0.031 by rho UL by mu to the power 1 by 7, that is given. This is the CD based on a local velocity, this is the CD net, that is the net effect on the plate. What is the equivalent CD that you have to find out. Okay. So to find out the CD, what you require? You require to find out what is the total drag force. So to find out what is the total drag force which is there acting on the body, how you should go about it? See, if you take a thin strip, say at a distance y, you take a thin strip of width dy. What is the drag force that is acting on the strip? See, why we are taking such a strip? Because we want to use our knowledge of boundary layer for flow over a flat plate. For flow over a flat plate which is oriented just instead of this, say oriented in such a way that a uniform flow is flowing on the top of that, then the reference drag coefficient is based on a uniform u infinity. Here as if the u infinity which is coming on the top of this plate is varying, it is varying from 0 to u infinity as you are moving along the height of the plate. So if you take a small strip over which the local u infinity is the local u, what is there, what is this u? So then if you calculate that what is the local drag force, the local drag force is the local CD into half rho local u square into the area L dy. Of course in practice if it is a slender plate like this, fluid is flowing on both the front and at the back, so you may multiply this by 2 for the two sides, and you can substitute CD as a function of u, and the total drag force you may integrate dFd from y equal to 0 to y equal to delta, and u as a function of y is given. So that you have to substitute for doing the integration. So I am not going through all the integration, but if you calculate the total drag force, it is 0.031 into 49 by 62 into rho nu to the power 1 by 7, L to the power 6 by 7, u infinity to the power 13 by 7 into delta. This is the final answer to this problem. And of course the net CD is something which is artificial. What is more important is the drag force, because you may just use any reference velocity. Say you may use the reference velocity as u infinity and very easily find out the CD by the drag force divided by half rho u infinity square into delta into L is the area of the plate. So, but important is what is the drag force effectively, that is what is more important. Let us work out another problem. So, you have a sphere which is moving in a liquid, the sphere has the density as rho s and the liquid has the density of rho, the radius of the sphere is r. So, you have to find out how the velocity of the sphere varies as a function of time if it starts from a velocity v0 at time equal to 0. Assume that it is moving in the vertical direction. Okay. So, now if you see, just if you consider the free body diagram of the sphere. So, what are the important forces that you see on the sphere? What are the important forces that you see on the sphere? So, if you draw the free body diagram, you have the weight, you have the buoyancy force and drag force. So, if it is tending to move upwards, the drag force is trying to make it move downwards. So, when we say that when the sphere is tending to move upwards, it means relative to the fluid. That means it might be so that the sphere is stationary, but the fluid is moving downwards from the top, it is all the same. But when we are writing equation of motion for the sphere, we are writing its velocity as velocity of it relative to the fluid, that means as if the fluid is stationary. So, if it is moving upwards relative to the fluid, then you have the drag force. So, you have the buoyancy force minus the weight minus the drag force is equal to the mass of the sphere into dv dt, that is the Newton's second law, right. So, of these things, the buoyancy you can very easily write. What is the buoyancy? 4 by 3 pi r cube into rho into g minus 4 by 3 pi r cube rho of the sphere into g. Drag force, it depends on the relative velocity, that is what is important. So, you cannot say what it is, you can just write it as say CD into half rho v square into the reference area. So, that is pi r square, right. Again the projected area is the reference area for these cases. So, not 4 pi r square, that you have to keep in mind. So, that is equal to 4 by 3 pi r cube into rho of the sphere into dv dt. So, the whole attention now is that what is the CD, right, and that depends on the Reynolds number of flow. So, this is a function of Reynolds number. If the Reynolds number is very very low, say Reynolds number less than 1, then the Stokes law is approximately valid. So, if Reynolds number is much less than 1, you have the CD is 24 by Reynolds number based on the diameter of the sphere, and there will come another velocity. If on the other hand Reynolds number is very large Reynolds number, CD may be approximately a constant independent of Reynolds number, because at very high Reynolds number we have seen that the effect of the form drag for bodies of with curvatures become more and more important, and the reason is as you increase the Reynolds number, what happens? What happens to the boundary layer? Boundary layer becomes thicker or thinner? If you increase the Reynolds number, the boundary layer becomes thinner. So, when the boundary layer becomes thinner, then when the surface effects of the fluid are there, they now penetrate into the outer fluid outside the boundary layer, and they may perturb it sufficiently, and that of course is it becomes more and more important. So, form of the geometry of the surface tend to become more and more important as you increase the Reynolds number. Now, at very large Reynolds number, CD is approximately a constant independent of Reynolds number. So, if you draw say CD versus Reynolds number for flow past a sphere, so what you will get out of this? So, what you get is something approximately like this. So, let us say we plot with a log of Reynolds number. So, CD equal to 24 by Reynolds number, if you plot it as a log of Reynolds number, it will be like a straight line, but that is valid only for very low Reynolds number. Then there is a significant deviation from this, and so it will come down like this, and there will be a sudden transition as at a particular Reynolds number when the CD goes down. Before this transition, the CD was approximately as a constant. So, it is not really a exact constant, but it is almost like an asymptotic, like it is almost approaching a constant. Then suddenly there is a transition, again it increases. This is roughly say for a sphere, maybe it is of the order of 10 to the power 5, this Reynolds number. Now, what happens here? Here there is a transition to turbulence. Because of a transition to turbulence, what happens? The boundary layer separation is delayed. We have seen that, like when the shape of the body is important in terms of the form drag, boundary layer separation is what matters, because early separation will induce a lot of form drag, but later separation will reduce the form drag. So, boundary layer when the boundary layer becomes turbulent, the separation is delayed. So, it reduces the form drag, and since at very high Reynolds number form drag is what is important, the reduction of form drag is what is prominent here. But beyond that, if you increase the Reynolds number further, then many interesting things may occur, because I mean it is a change of the state of turbulence from one state to another state, where the point of separation again shifts more towards the upstream. So, and then that is why, so this is all related to the boundary layer separation. So, what we are trying to understand is that towards the high Reynolds number for flow past bodies with curvature, the boundary layer separation is a very important phenomenon that dictates the total drag force. And the similar behavior is there for flow past cylinders, and let us try to understand what happens for flow past circular cylinders as a special example. So, we now look into some of the animated representations or movies related to flow past circular cylinders. So, one by one we will see, and we start with a particular visualization where it is almost like a potential flow. So, if you see that these green colored lines, these represent sort of streamlines, and if you see that these streamlines are very symmetrically coming from one side, and they are also symmetrically merging in the other side, the front and the back side. So, almost a perfect symmetry is maintained. So, just like what a potential flow could predict. Now, if you increase the Reynolds number, what happens? So, let us say the Reynolds number is increased beyond say 4 or something like that. See, at very low Reynolds number, the solution is almost like a Stokes flow solution. So, the solution does not consider the fluid flow or the advection terms in the left hand side of the Navier-Stokes equation. So, the advection terms, advection effects are totally neglected in that solution, but in reality the advection terms may be important typically as you go far downstream. And what happens is, see, physically what happens, the wall is a source of vorticity, because wall generates a velocity, cross velocity gradient, and that vorticity is transmitted within the fluid. So, if there is a strong advection, then the advection transmits the vorticity from one place to the another place and creates an asymmetry in the flow. So, if advection effects are totally neglected, that asymmetry is totally neglected, then vorticity is just diffused in all directions equally. but if the advection effects are there, then vorticity is preferentially transmitted or advected towards the wake side or the low pressure or the back side. And what is the consequence? So, whatever we showed as a visualization example, let us see it as a simulated example. So, if you see two eddies of counter rotating nature are formed at the back or in the low pressure region or in the wake side of the cylinder. We are talking about still low Reynolds number cases. Now, if you say increase the Reynolds number, you see certain interesting things. So, if you see, these are like staggered vortices which are forming. So, there is one row of staggered vortex interacting with another row of staggered vortex, and these are sort of rolling in the opposite direction. So, if we want to look into it in a bit more detailed manner, let us try to look into another movie, and with that movie what we will try to see is that what are the implications of these alternately rotating vortices. So, these alternately rotating structures, they have sort of an impression of footprints on a road, and this was first observed by von Karman, and that is why this is known as von Karman vortex street. So, if you see that basically what is happening is these vortex streets or these vortex lines, so to say, are interacting with the small eddies, the two counter rotating eddies which were formed close to the cylinder, because with increase in Reynolds number these vortices are coming very close to the back of the cylinder and they are interacting with those small eddies, and so alternately you are having sort of staggered rolls of vortices rotating one against the other. Now, so we will look into one interesting flow visualization of vortex stretching by using vortex shading. This phenomenon is known as vortex shading. That is, as if you have a flow in a cylinder, there is a flow past a cylinder. It is not just for a cylinder, it could be for body of any similar shape, but cylinder is just a demonstration. So, what we want to see first before going into the phenomenon of vortex shading in more details, that what types of vortex rolls are formed in the back of the cylinder. So, in the wake region or the low pressure region. So, like a animated description of the von Karman vortex street. So, just look into this very carefully, because this gives you an idea that what sort of vorticities are there, not in a quantitative sense, but at least qualitatively what is the nature of rotation of these individual vortices. And these vortices may be of quite complicated nature, and one of the important things that comes out of these experiments is that although the flow that came towards the cylinder was steady, but there is an unsteadiness in terms of appearance and disappearance and the frequency of the rolls which are appearing. So, although the incipient flow is steady, but flow at the back of the cylinder is unsteady, and it has a sort of a frequency or it has a sort of a periodicity in terms of the happenings. That is, the vortices are appearing, disappearing, again appearing, disappearing. So, vortex of one particular directional rotationality is appearing, then vortex of an opposite rotationality is appearing and the previous one is disappearing. So, alternately vortices of opposite signs are appearing and disappearing, and this phenomenon is known as vortex shading, and is one of the very important phenomena that you can see in flow past bodies of these shapes. Now, you can generate these types of flows in using computational techniques also, and this illustration will give you an idea of like how the vortices of different rotating nature are shed from the cylinder, as if they are being shed from the cylinder towards the fluid. So, you can see this clearly from this illustration. Now, we will see some more examples of the vortex shading. This is also an animated description. You can see that like alternating vortices are shed in the fluid from the cylinder, and that occurs for quite a large range of Reynolds number, and it is important for many reasons, because we will see through one example that what effect it has on the cylinder itself. So with a bit of a higher Reynolds number, this oscillation frequency this also changes, and we may have different experimental visualizations of these ones. So this is one experimental visualization, unlike the computational visualizations that we saw in some of the previous examples. This is an experimental visualization of the same thing. So we are just trying to look into this vortex shading phenomenon from different visualization perspectives. This is a computational way of like generating the similar type of behavior, and you can see from this example clearly that these vortices are as if rolling upwards and downwards like that, and that creates an alternating sort of frequency in the flow. So this is a flow itself is inducing some nature of rotationality or some nature of frequency in the system, and if you see that because of this sort of transience in the flow, the cylinder may itself start oscillating. So this is called as flow induced vibration of the cylinder. So it was a steady flow, it was not an unsteady flow. So if something vibrates because of unsteadiness in a flow, that is intuitive, but here the flow that was incipient to the cylinder was steady, but because of this physical phenomenon of vortex shading, you are now having some phenomenon which is occurring with a frequency, and that is forcing the cylinder to oscillate, and it may be very critical if that forcing frequency becomes same as the natural frequency of the cylinder, because that can give rise to a very high amplitude and sort of resonance, and that is one of the important consequences that may occur in a very strong fluid structure interaction. So you may have even multiple cylinders, and with multiple cylinders these types of effects you can see with like as if one effect is getting superimposed on the other. Here the symmetry sort of is very well preserved because the Reynolds number is not that large, but the symmetry may be destroyed by advection of vorticity if the Reynolds number is substantially larger. Now if you want to look at it in the form of a 3-dimensional structure, so you can see that by the example that we will be seeing here, let us try to see this example, maybe we just play it again. Okay. So if you see this is a 3-dimensional structure. So in the, so here the vortex shading phenomenon is shown in 3 dimensions, but the basic phenomenon is very similar to the 2-dimensional flow visualization observation that we have seen. Now if you want to say see the behavior, so these like the vortex shading frequencies are very critical for the design of a say structural system, and it may be possible that there is a wide range of Reynolds number to which the flow is subjected. So if we want to look into the flow past a circular cylinder, we could see that first there were some small vortices which were formed close to the back of the cylinder, then these vortices almost periodically appeared and disappeared and interacted with the main flow and created a vortex shading phenomenon. Now if you increase the Reynolds number to a very large value, then beyond a critical Reynolds number, which is roughly like maybe of the order of 5 into 10 to the power 5 or so, there may occur a transition to turbulence. So if we want to plot the pressure distribution around the cylinder, so when we plot a pressure distribution, we basically plot the Cp versus theta. So Cp is the pressure coefficient P minus P infinity by half rho U infinity square. So the physical situation that we are considering is there is a circular cylinder and there is a flow past this circular cylinder flow is coming with a velocity of u infinity and theta is a sort of angle measured with respect to the incipient flow. Now let us try to make a sketch, say from theta equal to 0 to theta equal to pi, the variation of the coefficient of pressure, which is basically a non-dimensional variation of pressure as a function of theta. First of all, let us plot it for a potential flow. So for the potential flow, if you recall that it was 1 minus 4 sine square theta for flow past a circular cylinder without any rotation. So if you want to make a plot of this, say this is pi by 2 and this is pi. So when theta equal to 0, this is equal to 1. So let us say this one, when theta equal to pi by 2, it is minus 3. So let us say maybe this one. So if you make a sketch of it like this, and then when theta equal to pi, 1 again. So something like this, okay. So this is potential flow solution. When will the potential flow solution be valid in terms of pressure distribution? If there was no boundary layer separation, then it would have closely followed this, because whatever is the pressure that is imposed from outside the boundary layer, same pressure distribution the boundary layer is supposed to feel, so long as the boundary layer theory itself is valid, that is so long as there is no boundary layer separation. But if the boundary layer separation has occurred, then so if the boundary layer separation has occurred, so it all depends on whether the separation is early or late, and for that let us consider say two Reynolds number. One is Reynolds number, these Reynolds number are based on the diameter d of the cylinder, so RED. Let us say one value we take as say 2 into 10 to the power 5, another Reynolds number we take as say 7 into 10 to the power 5, and let us say in between there was a transition. So let us consider that 2 into 10 to the power 5 is the laminar case. So if it is a laminar case, let us try to make a plot of that. So if you compare these two, in which case there will be a earlier boundary layer separation? In the first case, right, because the turbulent boundary layer has a greater momentum to sustain the adverse pressure gradient, so its separation will be delayed. So we expect usually that the separation will be there in the region where the adverse pressure gradient is felt. In reality, in the region where there is an adverse pressure gradient that is felt, there occurs a backflow, and the effect of the backflow is propagated even a bit in the upstream direction, so that the separation in the practical case for a flow of this Reynolds number regime occurs at roughly theta equal to 82 degree, that is the practical observation. So when till the separation has occurred, maybe it will come or it will not show a lot of deviation from the potential flow theory, but as it comes to a separation, it will show some sort of deviation from the potential flow theory. So this is Reynolds number equal to 2 into 10 to the power 5. See, after the separation has occurred, the Cp is roughly a constant. That means the pressure in the low pressure region or the wake region after which the boundary layer separation has occurred is almost like a uniform pressure which does not change further with theta, and it is typically a low pressure region. When it is 7 into 10 to the power 5, say it is beyond the critical limit or the threshold limit. So then the separation will be what? It will be further delayed, and typically this separation may occur close to 120 degree or something like that, maybe 118 degree, this type of angle, and till that limit. So if we draw that line, So, till that limit it will follow very closely to it will follow very closely the line which was there for the potential flow solution, and then when there is a flow separation it will come to a constant CD which is independent of the constant Cp which is independent of the angle theta, that is a constant, the pressure in the wake region is almost like a constant. So, this is Reynolds number equal to 2 into 10 to the power 7, and these angles are like roughly for the angle from which this change of behavior is observed depends on the separation. For laminar close to 80-82 degree, maybe for turbulent close to 120 degree, something like that.